I was going to say good morning to everybody, but I see most of the attendees this is going to be, I guess, fairly late in the afternoon, if not the evening, for a number of you. But thank you very much for inviting me to come and talk to you today. So Natalia and Doug, thank you very much for organizing this. It's really nice to kind of see how healthy and large your group actually is. It's quite a large group of people who actually pitched up today for your workshop, and I wish you all the best for later on today as you start diving in deeper into the applications of your bees algorithm. I've kind of been invited along today to talk a little bit about how we see our customers using optimization to kind of improve their solutions, whether that's in the engineering or the science space. My name is Rory Adams. I am what we call a customer success engineer. So I work in the academia team at Mathworks in the UK, and I support academics who are using MATLAB and Simulink as part of their teaching and or research. So basically just trying to make sure that they're getting the most out of the products. Couple other things on here is that I've actually been with Mathworks for nearly 10 years. For quite a long part of that time, I was part of the commercial team. So I worked as technical pre-sales, helping customers to understand how they could solve their problems using our products and our solutions. And then for many years also working as a consultant, where I actually went into the customer's organization and helped them solve their problems using our products and our solutions and get them up and going quickly. But today we're going to talk a little bit about optimizing engineering and science solutions, as I mentioned. A couple of things that you may or may not know. So firstly, I'm from Mathworks. People don't always necessarily associate Mathworks and MATLAB, but that's really what it is. MATLAB and Simulink are the two main platforms that we produce. I'm hoping most of you are familiar with MATLAB in some way, if not using it day to day, hopefully. But you should already be aware that it is a platform that we use for algorithm development, numerical computation, data analysis, and the like. There's also Simulink. I'm not sure how many of you are actually familiar with Simulink. You've seen it more in sort of control design and system design space in engineering. But it's a block diagram approach you can see there for designing, simulating, and testing systems, and then also deploying those systems to hardware. So those are our main two platforms that primarily get used. Now, what you might not know is that Mathworks as a company is a global company. We have over 5,000 staff throughout the whole of the world. Headquarters are based in Natick, but we've got very large offices in the UK, most of the European countries, in India, and a few coming up in East Asia as well. We have over 5 million users across industry and academia across the world. So we have a very large user base. And we also have, we are a privately held company, which is very profitable. And being privately held means we are able to actually focus very heavily on our people and our users to make sure that we're delivering the tools that are going to help them succeed. Now, you may not be aware, but our software is used to simulate, design, and test systems throughout many different industries. So from things like the cars you drive, the planes you fly, to the smart devices that you make use of every day, to the consumer goods that sit in your house and you make use of. All of these systems are designed, tested, validated, and analyzed using our products. All right. And we find that the engineers and scientists who are using our tools are continually making massive breakthroughs in the way we live, work, and learn. So that's from things like electrification, where we're seeing a move to things like solar power and clean energy, to a lot of work that's happening around autonomous systems like autonomous vehicles, and also when you start looking at applications of AI, such as the advanced prosthetics example you see up there, where we're starting to bring AI into the real world products and solutions that people start to leverage. All right. What you may not also be aware of, I have interesting conversations sometimes with people in academia where they seem to have a perception that MATLAB is a tool for academia only. While it's quite the reverse. It's very much an industry-focused tool, and we have users across 15 different industries, if not more. So some of the key ones you see here are things like aerospace and automotive, through to financial, semiconductor, medical devices. And in fact, you could most probably name any industry, and I could think of a person or a company I've gone to actually talk to and just to analyze what problems they're trying to solve and show them how they could be using our tools as a solution. All right. But if we now go back and think a little bit about optimization and why engineers and scientists are using optimization and how they're using it, well, I'm pretty sure most of you are in the optimization space. It should be fairly clear that they're typically trying to find better or optimal designs and decisions. Now, I guess an interesting thing is many people would think that they're just purely looking for an optimal design and decision, but it's amazing how often in industry, just a better solution is often a good place to be, as it can result in huge savings. Now, if we think of some of the applications we see, so the classic things of automating decisions, which you might see for routine tasks like trying to find shorted paths for delivering goods. There's also the area of trying to accelerate the rate at which you can find designs for your system. I don't know how familiar you are with the Bloodhound. It's the supersonic car attempt that they're busy designing at the moment. It's a little closer to my heart because they're going to try and run it on the salt pans in South Africa, where I'm originally from. But I was actually remember working with them when they had an issue with the design of the vehicle, one of the early phases, where as soon as they started to get to Mach speeds, the wonderful downforce they had at the rear of the vehicle started to turn into lift force, which is not an ideal solution when you're trying to travel 1,000 miles per hour on the surface. It was a rather complex design they were trying to adjust. So we worked with them to apply some optimization techniques and some sort of surrogate modeling to find a better design structure at their back, which they were able to do. So it was kind of a mixture of computational fluid dynamics and optimization applications there. But this is a case where we see a lot of our engineers kind of using optimization. Another one is if you're doing trade-off analysis, where you've got sort of thousands of dimensions that you're working with. It's almost impossible to do that iteratively or a trial and error approach, and optimization can really help there. And then another one that we often see is where we've discovered non-intuitive designs and solutions. So here I've said a design, but really you can think about a solution for the operation of a plant and etc. You will find that some genetic algorithm, in this case, it was a genetic algorithm was used to design. This was actually an antenna here. And I'm hoping most of you would agree with me that I wouldn't expect an antenna designer to naturally pick that layout as a good configuration for an antenna. This was actually produced from using a genetic algorithm. But in the same sense, using optimization techniques can explore areas where people might not have normally gone into. And you can come up with some rather interesting and novel designs and solutions, which turn out to be more optimal than the classic designs. All right. So what I'd like to talk a little bit about now is just some of the nice use cases that we have where we've seen industry users make use of optimization in MATLAB to sort of get optimal solutions and better solutions for their products. And so the number of people who are using optimization within MATLAB is extensive, massively extensive. Unfortunately, though, I can really only talk about the groups that have already shared a user story with us, which is kind of why I've selected down to these two. But there are a few in here that would be worthwhile to kind of bring up. So Building IQ, they've built a real-time platform. It's an energy optimization platform. They were looking at the heating and ventilation systems within buildings because it turns out that for large-scale structures like office blocks, etc., they account for about 30% of the production, or sorry, 30% of the energy utilization across all buildings in the world. And one of the primary contributors to that are the HVAC systems, because they're not always well designed for, they don't take into account ambient temperatures, don't always take into account the thermal properties of the building. So they can be quite inefficient systems there. They ended up building mathematical models based off a whole bunch of data that they'd recorded from the buildings. So there's one level of optimization where they're doing parameter fitting to get to fit the parameters to the mathematical models. But then on top of that, they then started bringing in real-time weather prediction information and weather data, and running these multi-objective optimizations across many different non-linear cost functions and constraints to continually optimize the energy efficiency. And with this system, they've actually been able to reduce the energy consumptions by the buildings by about 10 to 25%, which is a very nice story, especially in our world of trying to lower carbon impacts. Then you switch across to a very different application. So Realtek are a semiconductor firm, and they were designing these high definition digital audio codecs, also for processing high digital audio systems. And they used a huge stack of our tools actually around digital signal processing to design the algorithm. They were using fixed point designer to try and then digitize that into fixed point data types for when they're trying to target these semiconductor devices. And they came up with a design. But the interesting part is once they had that design, they actually then used optimization to enhance the effectiveness and were able to reduce the size of the chip that was needed. In doing so, they actually were able to get to market faster than anybody else, and it's believed they have about a 60% share in the global audio codec market now, because their ability to get to market quicker. And so this is, I mean, a very, very interesting idea. You would not normally think of people starting to bring in optimization into this sort of a designing of a chip or a DSP solution for a system. Right. Another one I'm going to bring up is perhaps closer to some of the applications that you guys will see with these algorithms. So this is, if you look at STEIWA, I think that's how you say it. I've never actually heard anybody say it the same way twice, so I'll stick with that. But this is a large high-performance automation plant that is actually based in Austria. And what they did is they pulled a huge volumes of data from all their sensors on their devices and did some automated analysis and data analysis on that. I mean, we're talking about gigabytes and gigabytes of data being pulled from these devices. And they used optimization techniques to plan optimal trajectories for the robotics components so they could maximize the total production output. So this is now using optimization within those automation and production plant scenarios. There's also PPT, the exploration and production side, where they were looking to optimize their gas field production. So they were looking to obviously maximize the production and also generate accurate forecasts while sort of really accounting for some very, very strict operational costs, constraints that you have within these large-scale gas and oil industries. Something a little bit interesting here, I guess, is when they were doing this approach, they really weren't sure which optimization technique was going to give them the best solution. So this was a group that actually tried multiple different optimization techniques to try and find eventually what they were looking for, including some mixed integer linear programming that they were using as well. So we're seeing it so far like a mixture of perhaps people who are very optimizational or very mathematically aligned. So where we had the building IQ, we're starting to see people who are perhaps more on the semiconductor and digital signal processing fact. And here's another case where we're having non-specialists where they don't really know which algorithm is going to work best and they need to try it out a bit. A couple other interesting ones. So in this world of robotics, the ClearPath Robotics, they built these auto robots. Now it's very classic kind of robotics and autonomous system where they've got what we call LiDAR detectors. You get those on a lot of vehicles these days. And those were used to understand their environment and try and identify some of the packages that we needed to get. There's the normal robotics and autonomous system designs that you need to do. So on top of all of that standard operation, they then also used optimization techniques to ensure that when these robots were working as a group on a mission to move one object, one component from one floor of the warehouse to another, that it was certain metrics were minimized, and that could be things like the total distance traveled or the total time taken to get there. And then another interesting one from the science area, Tesla. So this is a solar orbiter that was sent up. It's got a, part of the European Space Agency, it's got a special shield on the one side. And what they needed to make sure was that that satellite, or that orbiter, stayed at the same altitude as it was going around orbiting the sun, and that it always had the shield pointing at the sun, so that the instruments inside were protected and they were able to get the maximum benefit from the devices inside. Now, the control in there consisted of two things. There was a chemical propellant, and then there was also some reaction wheels. So there were two different ways they could control the orientation and the altitude of that orbiter. And they brought in the optimization to make sure that while they were designing the controls and using these two different ways, they could actually minimize the propellant consumption that was used. Because obviously, the more chemicals you have to send up, the less other instruments you can pack into the same device to be able to actually deliver it out into that orbit. So this is another interesting one where you're thinking perhaps these are control engineers and normally control strategy, but they're now starting to bring in optimization to try and improve the behavior as part of their control. So Mathworks as a provider of tools to customers in both academia and in industry, we provide tools based on what their needs are. And if we go and look at a lot of the customers out there, you'll see things like in all those scenarios, we had people who are perhaps very familiar in the digital signal processing domain, or robotics and autonomous systems or controls, but they aren't necessarily experts. So you have somebody sitting out in industry going, I need to find the optimal, or if not optimal solution, a better solution to what I'm trying to do. But I'm not an expert at optimization. I know my domain. I can use MATLAB to do my DSP. I can use MATLAB to do my robotic systems or my machine learning that I'm trying to do, data fitting, but I'm not an expert in optimization. What I do, how do I get the best of what I'm trying to apply? And I work on very complex problems. Surely I need very robust and powerful algorithms to be able to solve my problem and make sure that the solution I'm getting is really going to be optimal. So these are kind of the thoughts. It's a very simplified approach, but these are some of the major trends that we see within our customers out there. So we do a lot of work to try and make sure that these needs are actually met. Perhaps I don't know if anybody here has ever used MATLAB to do optimization. So this might look familiar. You would end up at the top defining perhaps your constraint functions, your cost functions that you want to optimize. You then need to put in some of the constraints. So you'd need to take the constraints and jig them into some sort of matrix form or vector form to put them in, and then you'd pass them into a solver with a bunch of arguments in a specific order and as it's been adjusted there. And then if you wanted to use a different algorithm, then you most probably had to restructure the way you're defining it a bit. So this was a bit of a hindrance. So we've moved to this problem-based approach for defining the problem, where you then have this sort of modeling language that you can use, and you can then express your problem. So for example, if you look here, in a form that is far closer to the mathematical problem you were actually trying to solve and implement. So this makes it far more intuitive to read and understand and implement. You then just pass the problem into a solve, and what the solve will do is now it has the ability to start to auto-identify which solver should be applied to the problem and doing that. But then at the same time, you could pass another input into the solve command where you specify exactly which optimizer you want to use. So it's now much easier to switch between different optimization algorithms to try and see which ones are going to be providing the best benefits. So this is a case where we've listened to the customers out there and have now provided a way that makes it easier for them to set up their problems and start to cleanse the problems. It also has some other benefits, like you can do auto differentiation because you've got this modeling language approach. Another thing is obviously we then want to make sure that we are updating and improving the problem types and algorithms that are made available to our customers. And these are very much driven by what they need. So you can see cases where we introduce within the newer versions some new algorithms within these areas, or even start then making updates and improvements to the existing ones, whether that's performance updates or support for parallelization and etc. So these again, and these changes are typically driven by what we see as customer needs, what they're trying to solve and the problems they're trying to solve out in industry. And then finally, the other thing we always have to do is provide examples. Examples. I don't know how many of you here use MATLAB. I'll check with you later, but it's very well known for its documentation. And people always say our documentation is great and they love it. And the way I've always used the documentation is if I look at a function, I'll look at how it's called, and then I immediately jump down to the examples. And I look at the examples. How is it used? How is it used? And then I will go and look at the examples within the documentation separately to see how we can do all of this stuff. What I've done here is I've also just shared, so these slides will be made available with some of the links in here. So here are links to a number of the examples that we ship, as well as some examples that we provide both through our file exchange and some of the how-to videos with demos available. So I'll leave it up to you guys in the audience if you decide you want to try and apply the Bayes algorithm to some of these various examples and see how it behaves in terms of comparison to and do some sort of validation of the algorithm. You're more than welcome to take these and try those out. But examples and well-written examples are a good way to help people pick up the algorithms that you develop and actually start applying those to industry. Because the worst thing for somebody who's trying to solve a problem is if it takes them 3 days to work out how to use the tool to solve the problem. They want to get going straight away. They want to pick it up and run it and be able to apply it to the problem and start getting some results immediately. So by listening to the customers and providing them with the tools that they need, we find that we can really accelerate the way that engineers and scientists are solving their problems. And by coming together, we can really help them find better solutions through optimization. Thank you, everybody.